So the next speaker is Thomas Weber. Thomas, can you please put on your camera and start sharing your presentation? Great. Try to share the screen.
Yes.
So also Thomas is from the iCube laboratory in Strasbourg. Sorry. And he will be presenting us MISTIC, a prediction tool to reveal disease-relevant deleterious missense variants. So your stage is yours, Thomas.
Okay, thank you. Okay, hello everyone. It's a great pleasure to be here. So my name is Thomas Weber. I'm third year PhD student in the CSTB team at iCube Lab in Strasbourg. And today I will present our latest published project called MISTIC. So a few words on context. So there are about 6,000 known genetic diseases, where half of them were resolved with known molecular cause. And the advances of sequencing technologies enable both identification and characterization of genetic variations. So today we can use as a daily routine basis use exome sequencing, which consists to sequence 1% of the genome, 1 to 3%, with sequences coding for proteins. And limitations no longer lie today in the generation of data, but rather in the analysis. So what is exome sequencing? It's the search of the variation responsible for pathology at the borders and within the coding regions, with the final aim to evaluate the impact of each variation according to its consequence on the gene. So there are about 120,000 genetic variations in a typical exome. There are different classifications. I chose to present classification by impact. So there are a small amount of variations with a high impact on the exome, 100 of them, which can affect and impact splice site, for example, stop or start sites. There are also variations with a moderate impact called missenses that lead to a modification of the translated amino acid at the protein level. And there are about 10,000 missenses in the genome. And finally, in exome, you can find 110,000 genetic variations with a low impact, for example, not leading to a change of amino acid called synonymous or affecting intronic regions. So there are real interest on missenses due to their large number in the exome, and they represent more than half of the pathogenic validated variations in the current state of databases. And before the 2000s, researchers and clinicians performed a manual expertise to switch today to a semi-automatic management due to the advances in database mining, AI, and in silico predictions, which lead to the development of MISTIC for missense deleteriousness predictor, which was recently published. So MISTIC bring one major improvement in the 3 different components of machine learning. So first, on data, we use one positive and one negative set. For the positive set, which consists of pathogenic variations, we use 2 different clinical databases, ClinVar and LGMD, with an amount of 250,000 variations. And concerning the negative data set, benign variation, genetic variations, we use GNOME-AD population database composed of 125,000 of people and more than 6 million of missenses. And first improvement here on data is the diversity represented by the 3 different databases and the representativeness compared to reality in a standard exome. And we also applied different filtering steps to recovered more than 11,000 relevant genetic variations for each data set. Secondly, concerning features, we used 4 main categories of features. First, allelic frequencies for population and continental subpopulations. We also used conservation measures at 3 different levels, primates, mammals, and vertebrates. We also used functional measures, with some of them used for the first time, and finally, pathogenicity predictors. And the second improvement here on features relies on relevant selection and redundancy removal that leads to a performance improvement with 113 final features selected after a recursive features elimination step. And finally, concerning algorithms, we used 2 different families of algorithms, logistic regression and random forest, combined for the first time in the soft voting system. And this soft voting system also leads to an improvement of the performance. So how MISTIC was evaluated? So we used the classical 10% of data not used during training in machine learning and AI, so which is composed of more than 1,000 genetic variations for positive and negative data sets. We also built 2 different pathogenic variation sets. First, which focused on novelty with clean new, which is composed of recent genetic variations never seen either by MISTIC or other competitors. And we also used DOCM, a cancer database, to analyze the diversity performance of the predictors. And finally, concerning negative variation sets, benign variation sets, we use the remaining genetic variations with allelic frequency and gnomosity not used during training to evaluate the impact of MAF at different levels, from singleton to one classical 1% of allelic frequency in population. And we computed 3 different specific population data sets, English, Swedish, and Kuwaitis, to analyze the impact of absence of allelic frequency in genetic variations. So concerning the VAR test, first data set, first evaluation set, you can see with this receiver operating heuristic curve that evaluates the performance of binary classification model at different classification thresholds, that MISTIC is the only one classifier predictor to pass the gap of 90% of area under curve, which leads to a best overall performance for MISTIC compared to other tools. Concerning datasets with presence of MAF, we evaluated the impact of MAF from singleton to 1% of allelic frequency across global population. And you can see here on 3 different metrics. AUC again, F1 score that takes into account false positives and false negatives, and log loss that takes into account the divergence of the probability compared to real level, that MISTIC has the best performance in presence of MAF. And we also checked in absence of MAF that we had a good performance. If you want to sequence your genome tomorrow, maybe you will find a private genetic variations that have not been sequenced yet, and that are not in the current state of database, in the 125 individual exomes. So here you can see that the performance again on these 3 different metrics of MISTIC is highest compared to predictors. So MISTIC has the best performance in presence and absence of MAF. So then we evaluated MISTIC on a concrete exome scenario analysis on 2 different scenarios. First, on simulated exomes, with more than 1,000 exomes recovered from the 1,000 genome project, where we randomly injected a pathogenic variation in each of them. And second scenario, where we scored real patients' exomes, myopathy exomes, 15 of them recently resolved from a collaborator in the context of MyoCapture project. And with two different goals. First, to reduce the percentage of variations with uncertain status, and second one, to obtain the best possible ranking for the causative variation for the pathology. So how did we proceed? We recovered all the missenses in the exome, and then give a probability ranging from 0 to 1 to each of the missense genetic variation. Then we take the list and order the score in an ascending manner. And the idea is to have the rank the lowest as possible. And we take out the rank of the causative missense, either experimentally validated or injected, randomly injected. So here you can see on simulated exomes that MISTIC had a median rank of 2, and the mean rank, which is the best performance, and the mean rank of 14, which is the second best performance compared to other tools. And on real myopathy exomes, we have a median rank of 12 and a mean rank of 14, which is the best performance compared to other tools, existing tools. So MISTIC optimally classifies the causative variations. So to conclude, we developed a new predictor that evaluates the pathogenicity of missense genetic variations. We bring one improvement for the different components of machine learning, data, features, and algorithms, which lead to performance improvements in various scenarios in presence and absence of math. We also improve the ranking in exome analysis with a median top 12 ranking on real exomes. And in the future, we will exploit the MISTIC model in a framework of integrative exome analysis program called VARScript that combine prediction model, heredity scenario analysis, and literature monitoring. We will also develop new versions of MISTIC, which integrate new features, larger population databases or exploration data. And we will also reuse the methodology developed for MISTIC and for the data processing of genetic variations for the development of other models, such as aesthetic, that focused on spliced variations. So thank you to the funding agencies and to all people which were involved on the project, and especially to Kersley, which is a co-author on the paper. Thank you for your attention.
Thanks, Thomas, for the nice talk. So if you have questions, post them in the Q&A. Maybe I can start with the first question. So you combine logistic regression with random forest. Did you test also them separately, and did you test other combinations in order to see that this one was the optimal one? How did you arrive to this specific combination?
Yeah, maybe I can show additional slides to explain. So yeah. We trained, sorry for the French, but we trained 10 different machine learning algorithms with different combination of them, and we analyzed on for example, presence and absence of math, that the combination of algorithms had the best overall performance. For some combination of them, for example, random forest and gradient boosting, we had the best performance that the current combination, but especially on with presence of math. But the performance was really reduced in absence of math. So we choose a good balanced performance in different scenarios.
Okay, thank you. And then we have 3 questions in the Q&A.
Okay.
So the first one from Fanny, thanks. You use the same amount of deleterious variants and benign, but without the genome. We would expect that there are much more benign than deleterious. In other studies, some that identify motifs within the genome, they show that increasing the number of control sites increases the ability to identify their sites of interest. Could increasing the number of benign sites could help the identification of deleterious sites, like you would know better the features of sites that are benign?
So I don't know if I'm answering correctly the question, but we tried to train with an unbalanced way, for example, to have 50 benign variations against 1 pathogenic variations in our training set, because we are not limited yet in population variations, but more in pathogenic ones. But we did not have an increase of performance, so we did not retain this strategy. But we tried also during the development of the model.
Okay.
I don't know if it answers the question, but
I think it does. In case Fanny, you can write back for additional details. Pierre, thanks a lot for this work and this nice talk. What about time performances?
Okay, concerning time performances, we don't especially check the time performances because we pre-computed the MISTIC's probability for all of the 74 million of possible missenses in the genome. So we take out the definition of CADD, which is a gold standard in terms of variant prediction, and which give a list of all possible genetic variations in the human genome, and take all the missenses and score them.
Okay, then Thomas, have you been able to reverse engineer what was driving the improvement of your method as compared to other available? The added features, which in particular? So when you show the performances that are higher, do you know like what is the element that makes your method work better than others?
Okay, so like how do you say? We use like CleanPred the allelic frequency, which so MISTIC is a second program to use allelic frequency directly in features selection, and allelic frequency has high improvement in terms of performance, and it's shown, for example, here in weight, especially for the random forest. I don't know if you can see here,
yes.
For global math, that there is a large weight for random forest that significantly improves the performance. But the strength of our model also is illustrated here, because you can see the great complementarity, which is not because math, for example, is not used by the logistic regression. So if you have a biased math, for example, you will be corrected by the logistic regression.
Okay, so do you think also the fact that other methods choose just one methodology and you combine two complementary ones could be the key point? Okay, thank you. And then Claire, have you tried to test MISTIC performance on top med data?
No, we didn't try yet, but maybe in the future it will be interesting, yes.
Okay, and then Anthony, did you try to use an ensemble methodology to combine prediction from MISTIC and other methods to potentially gain even more? So combining other methods that you have benchmarked with yours.
To ensemble method command. So we already integrated some predictors that are not used. So not how can I say? We already integrated some predictors, for example, MetaLR, MetaSVM, VEST4 in MISTIC. But they have not the highest way, for example, in random forest. So it could be interesting to integrate other methods, but I think MetaLR and MetaSVM already integrate some of them.
Okay. Yeah, especially if in the benchmark you have some methods that are quite complementary in respect to MISTIC,
yes.
Maybe including them could be a way in order to increase the performances, having combining, having an example of
yes.
the methods rather than single one. Okay, maybe I have time just for one last question. In your perspective, you talk about the possibility to integrate expression data with MISTIC, that you plan to do this. How do you plan to do it?
Yes, so we are currently working on it to check if a nucleotide is used in all the tissues with the GTEx database, which is quite known now, to check, for example, if the nucleotide is specific to muscle or used in all the tissues, and it could be interesting to link that, for example, to phenotypes and to check the impact, the global impact on the genome and on the pathology.
Okay, thank you. So I would thank you for the talk, Thomas.
Thank you very much.